Welcome to part 2 of lesson 2 in dimensional analysis about pi theorem. So in part 1 we introduced the idea of physical models. We talked about the principles of similarity, geometric, kinematic, and dynamic similarity. Geometric similarity has to do with the shape of the object. Kinematic has to do with things like velocity, things that are changing in time, and the dynamic similarity has to do with forces. Yeah. So forces when we start to talk about force. In this lesson, and we talked about pi theorem and how pi theorem, if you know pi theorem, how you can find some non-dimensional parameters and like you use this non-dimensional parameters to design your experiment and present your results basically. So how to find this non-dimensional parameter? Well, there is something called the Pickingham pi theorem. Uh, we did this actually in lesson 1 in dimensional analysis when we were talking about this Darcy experiment and Coulomb experiment, but we did it intuitively. We didn't do it systematically. There is a systematic way of doing this. So basically, the other one was easy to do because it was like few parameters and like a linear relationship mainly. But in this one, you see here you have like more than like lot of parameters like the force, the density, velocity, the object, the shape object, which is expressed as like a diameter, and the viscosity. Okay, so we have more than one parameter. Yeah. And so it's not as easy as the other one, and like you could also have like it's not only one parameter, you could also have this non-linear relationships. Yeah, but how did we come up with this? Like how did we come up with let's do some drawing here. Yeah, let's select. Okay. Yeah, whatever. How did we come up with like this guy here and with this guy here? Like how did we know this? Yeah, delete this guy, we don't need. How did we know this relationship that like the drag coefficient, which is this dimensionless parameter? How did we come up with this dimensionless parameter and this one, like two dimensionless parameter? So here we call this bi term. So this is like bi one, and this is like bi two. So how did we come up with these two pi terms and how did we make them dimensionless? So if you check the dimension of this guy, to be exactly equal to the dimension of this guy. So basically like CD, the dimension of this one would be like is like dimensionless, yeah. And the dimension of this guy, that is like dimensionless, yeah. So how did we come up with this dimensionless parameter? And once we know this dimensionless parameter, we can see like the change of drag force, how like drag force is like changing with respect to all these other parameters. And you see here like you have this nonlinear relationship. So basically this is what we will do in this lesson. I will show you like the systematic I will show you like the systematic step, which is called like the pi theorem for finding like coming up with this guy and this guy and then using this. And in the next lesson, I will show you like how through like this pi term, how and something called like a scaling law, how you could scale back and forth between your prototype and the physical model. Yeah. So let's just start. Yeah. So like, it is the same problem which I talked about like last class. This like drag force of column, and we talked like this drag force, we talked it's a function. Remember we talked last class that drag force was a function of like the geometry of the object, like the diameter, for example. It was a function of so that's like the geometric similarity. It was a function of velocity when we talk about, and it was a function of density and a function of like viscosity. uh, so basically So basically, this is like what we did last time. So last time we choose the prevalent variable or parameters and write a functional relationship. So the functional relationship here is like we know that like the force, the drag force, that is a function of diameter. That's a function of velocity. That's a function of density. That's a function of viscosity. This has to do with the object. This has to do with the velocity of the fluid, and this has to do with the properties of the fluid, its density and its viscosity. Yeah. So that's the first basically thing in this step. Like when you have a problem like this, remember, like Darcy experiment, we did something similar. Yeah. Here you just need to write like your parameters. So here I have four independent variables: the diameter, the velocity, the density, and the viscosity. I have one dependent variable, which is the drag force, like here, this guy here, the drag force. So basically, you just this is just the dimension, not dimensionless. So here this is just the dimensions. Yeah. So here you basically so you can say here this is like D, this is V, this is force, like we can call it like that, and this is the viscosity, density, and this is the viscosity is usually rho and mu. Yeah, and the diameter, like what's the dimension of this guy? What's the dimension of like a diameter? So we know that this is L. Yeah. Velocity, what's the dimension of velocity? That's L over T. Yeah, so that's L T minus 1. Force, remember, that's like mass time acceleration. So that mass is like M. It's not clear. Makes this a little bit bigger. So that is like M. And then acceleration, that's LT minus 2. And density, remember, that's mass over volume. So that's mass over volume. That's L minus 3. We learned this. And viscosity, if you remember, like from the, you can, if you don't remember, you can derive it. That's the shear force over the shear velocity. You can drive it, or you can just check it in a table. So like I remember this from last class, so that would be something. I think you did this also in your homework or one of your practice problem. Yeah, so you get something like this. So you basically uh, uh, write like the dimensions of your. So that's the first step. The first step is like you write the relation between like your dependent variable and your independent variables. So here we have a total of 5 variables. Like that's the 5 of them, and you prepare like a table that looks like this. It's a very systematic. It's very easy. The most difficult part in this process, like in this pi theorem, is that like you identify the pertinent variables, the pertinent like dependent variables, and to do this you need to have like a physical understanding of like some understanding of uh, of uh, of the problem. Yeah. So that would be the most difficult part, and this you get this from your understanding of fluid mechanics, your understanding of structural analysis, or whichever problem you are solving. Yeah. So that's the first step. Yeah. The second step, okay, so you have like some new term here. Choose a repeating variable. So let's call this M to represent all dimensions, but not to include dependent variable or dimensionless variable. What does this mean? Okay, I mean, what is repeating variable? So repeating variables, these will be the variables that will repeat in your pi term. So like let's say like remember I showed you here in this problem we have like two pi term, like this would be one and this would be another one. So these would be like the repeating variables that would you expect them to repeat in this pi term. Yeah, that is like in each of these pi term. Yeah. So, but so how would I know? Like I have 5 variables here. Like how would I know which 3 do I need to choose as like my repeating variable? Like the variables that would appear in like pi 1 and pi 2. Yeah. So which one? How would I do this choice? Well, there are some rules you need to follow. Like the first rule, your repeating variable should not be your dependent variable. So your dependent variable is this one. Yeah. So it shouldn't be this one. So that's easy. So I cross out this one. Now I need to choose three. Like which three here to choose? Well, your dependent variable should represent all the dimensions. So I should select one variable that represent, for example, mass, one variable that represent length, and one variable that represent time. In order to achieve geometric, kinematic, and dynamic similarity. So with respect to geometric, so I can choose this one, like diameter. Yeah. So that's the diameter. So that will ensure geometric similarity. So my first variable that I will choose here, that would be d. Yeah. Well, what is the second variable? So I choose this one. Yeah. I should now choose something to represent kinematic or like time dependent. So something that has time, like all these guys has time. Like this has time, this has time, this has time, this does not. So I can check. So usually you select the velocity because we know kinematic is related about velocity. So that's my second dependent repeating variable. Yeah. Third, I should choose something that has mass. So the one that has mass, so I choose this one already. So I need to choose just like one of these, like two guys as my repeating variable. I will just choose density. It looks simpler, yeah. So I will just choose density. So basically, these are my three repeating variables. So in my pi one, it will has d, it was has v, it was has rho. My pi two will has d, v, and rho. Yeah. That is basically my repeating variable. So m in that case is equal to 3. Yeah, because I need like one for M, one for L, and uh, uh, one for T. Uh, okay. And now find the number of term, dimensionless parameter or dimensionless group that your physical relationship can reduce to. So now I want to find like how many terms. Like see in this problem I have 2 terms. In other problem, I told you you can have 3 or 4. Like, how would you know this? Basically, you 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 subtract your number of parameters from the number of repeating variables. So the number of parameters that I have here is 5 parameters. Remember, we have like 5 parameters. 1, 2, 3, 4, 5. Yeah. So this is like 5 parameters, and the number of repeating variables that is like 3. Because we have like 3 main dimension MLT. So like that's the uh, number. And again, like this is geometric that has like to do with L, V that has to LT minus 1 here. And that's rho that would be ML3 minus 3. So so here I'm representing the L, here I'm representing the T, and here I'm representing the M. Yeah. So now I have all my 3 dimension represented in my 3 repeating variable. Yeah. So now the number of pi terms, so pi terms, the number of pi terms, that would be equal to what? That would be equal 5 minus 3, and that will give you 2. Yeah. So that's basically the second step. Okay, so simple. So the first step, you write down this relationship. Second step, you choose the repeating variable. How to choose the repeating variable? Your repeating variable should represent, like you should include MLT. And they should ensure geometric, kinematic, and dynamic, like something that's mass dependent. Yeah. So here for this guy I choose D. For this guy I choose the velocity. For this guy I choose the density. Yeah. I could have also for this guy chose the viscosity, for example. Yeah, but that's simple. Okay. Now this is like step 4 is easy, but it's just a little bit tedious or a little bit time consuming. Yeah. So basically, how you form your pi terms. So remember, you have a total of 5 parameters. Yeah, that's like a total of 5 parameters and like 3 repeating variables. So let me write them here. So the parameter, what are the parameters? The parameter are the drag force, the D, the V, the rho, and the mu. And what are my 3 like repeating variables that I chose? I chose like my 3 repeating variables. I chose D, I chose V, and I chose rho. Yeah. So this is like 5, and these are 3. How do I form my PyTerm? Well, it's very simple. Like you form my PyTerm like these are the repeating variables, and like you add one of the non-repeating variables. That's your would be your PyTerm number 1. So I will say like Py1. That would be my repeating variable, which I can say like rho, for example, V, and like D, and one of my non-repeating variable, which is fd. That would be my Py1. Yeah. And here, Py2, let me make this a little bit smaller so I can write them side by side. Yeah. So let me make it a little bit smaller so I can write them side by side, might be easier. So Py1, that would be my rho v d, and like one of my non-repeating variable, which is like this guy, for example, and Py2, that would be like rho, my repeating variable v d, and like what my third parameter. So now I have all the 5 parameters represented. Yeah, rho v d, drag force, and viscosity. Okay, so what do I need to do? Remember, what is the objective here? My objective here is I know that this guy I need to make it dimensionless, because that's all what it is, dimensionless parameter. Like, so how could I make this guy dimensionless? Remember, from dimensional analysis, each of these guys has like a certain dimension. Yeah, so each of these guy has like a certain dimension. So to make this guy dimensionless, I need to like square this guy, or take square root of this guy, or take the cube of this guy, or whatever, so that all this term will become dimensionless. Basically, that's the whole idea. So like the whole idea here, I will like just put here like a power of a, power of b, power of c. Yeah. So basically, and same here, like power of a, power of b, power of c. So basically, I want to make these power like 1 over 2, 2, 3, or whatever, so that this term will become dimensionless. Similarly, I want to make a, b, c the same here, so that this term will become dimensionless. So let's look at it. Let's look at it in detail. So here, like let's see, for example, like this guy here, like Py1, we know like rho, we know what is the dimension of rho. That's like mass over L cube. Yeah, we know this, and then to the power of a. And v, velocity, what is the dimension of this? That's L over t to the power of b. And then diameter, that is just like L to the power of c. And the force, that is like m L t square. Yeah. So that's like mass over mass time acceleration. Yeah. Oh, sorry, that's not Py2. This is Py1. Yeah. Here, let's do this as like we'll do the same for Py2 here. So now what is the objective here? Now I want to, remember, I want to make, like for example, let me show you like an simple example. Like I want to make this mass cancel with this mass. For this mass to cancel out with this mass, this need, A here need to be -1, because if this is -1, this will go to the dominator, and then this m will cancel with the m. Similarly, I want all this s on the numerator to cancel with all the l in the denominator. And similarly, I want all the t in the numerator to cancel with all the t in the denominator. So for example, like for this to happen, the p need to be minus 2, for example. So if b is -2, then this will cancel with this. So you got the idea? And you don't need to, you can do it like just as Orgo, you can do it algebraically. So it's easier. It's always easier to do it algebraically than just what I described it here. Yeah. So to do it algebraically, so I know like this pi1, like the m is equal to 0. Yeah. It's dimensionless. L is equal to 0, and the t is to the power 0 because this all dimensionless, dimensionless, dimensionless. So that will give you 1. Yeah. And basically, here I can just like group all my m terms. So my m term, I have here a, yeah, and I have here 1, yeah, and this is like time. All my L term, I can group all my L term. So all my L term, that would be like minus 3a, yeah, that is like minus 3a, yeah, and that would be here plus b, yeah, and that here plus c, yeah, plus c. And then finally the t term. So I have like the t term. So like you look at the t term, I have like here minus b. Yeah, you agree? And here I have like minus 2. Yeah. So basically like what I did here, I just like group all the MLT. And I know that to make this equal to 0, then this guy need to be minus 1, for example. Yeah. So here, like what you do here, you just equate the power of all primary dimensions. So like I equate this to this, I equate this to this, and I equate this to this. That's what you do. So I have like m. So I equate the power of primary dimensions. So I have like a is equal to a plus 1. Yeah. And this will give me like a is equal to minus 1, for example. L, this is 0. Yeah. Is equal to minus 3a plus b plus c. Yeah. And then t. That's like 0 is equal to minus b minus 2. Yeah. So if you just like substituted like this guy here, okay, that will give you like 3a plus b plus c is equal to 0. And then like here, like b is equal to minus 2. So like you substitute like this guy here. Then if you did this, like you substitute this guy here, you substitute this guy here, that will give you like c is equal to minus 2. And then we know that a is equal to minus 1 and b is equal to minus 2. Yeah. So let's just see here what we did. So what we did here, we just were able to find like the power of a, that's minus 1, the power of b, that's minus 2, the power of c, that minus c, that will make all these guys like dimensionless. So we just like substitute this power back. So basically that will like pi 1 will be equal to rho, that's to the power of a. Remember like a here is minus 1, so rho minus 1. V to the power of b, which is b minus 2, that's like minus 2. And d, which is to the power of minus 2, d to the power of minus 2. And then here, this guy does not have anything. So, wow, I got it. Can you believe this? I just got my first dimension. Yeah. Similarly, I mean, I can do like the same here. I mean, for the interest of time, I'm not gonna like, I mean, do it. I will just like show you like the final answer. You can check your slide. Remember, like we have something. Remember, we have this guy here. We always have this guy here, like your course slide, like class notes, so you can check like the solution step by step. So here, for the interest of time, I will just like show you like the end result for this guy. So for this guy, like here for By 2, like I will do the same, right? Like I will do the same. So here for by 2, I got my, if you did this similar analysis, I got like A here is equal. You can do it, like, so you can pause the video and try to do it on your own. That's an excellent practice. A is equal to -1, B is equal to -1, and C is equal to -1. So just follow like the same step here, like do it with this guy, with the dimensions of this guy. And if I did this, then I get here pi 2, that's like rho -1, V -1, D also -1, and time my mu, my viscosity. Yeah. So here I got my pi 2 term, and I got my pi 1 term. Wow, we are almost there. Yeah, right? We are almost there. So that's like step 4. Yeah, we are almost there. So here again, like how to do this, just to summarize, you have like your repeating variable. These are like these guys here, you give them A, B, C, and then you have your remaining variable or like non-repeatable variable. So in that case, you have pi 1, you put this guy, pi 2, you put this guy. If you have like, if this problem, let's say, has 6 parameters, yeah, then you will have the repeating variable will be still like 3 if you are just dealing with LTM, less time and mass, but your remaining variable will be 3. In that case, that's like your practice problem. You'll have 3 pi. You have by 1, by 2, by 3. Why? Because the remaining variable will be 3. So you will like put whatever the repeating variable and your first remaining variable, that would be by 1, your repeating variable, your second remaining variables, that would be pi 2, and then your repeating variable and your third remaining variable, that would be pi 3. But that's not the case here. Okay, so now that is this like step here is you just find your pi term, and then like once you find your pi term, you can just like basically get your final answer. Yeah. And what is your final answer here? So let's just look at this guy. Yeah. So basically, let's just make this guy looks a little bit more beautiful than what it is. So like let's say like pi 1, that would be my drag force over rho v and like d square. Yeah. Do you agree? I just like make this guy look more beautiful. Uh, uh, and so that's my pi 1. And then so that guy, actually, if you know fluid mechanics, you would know that this guy has a term, it's called like drag coefficient, like CD. That's like my drag coefficient. Yeah. Now let's look at pi 2. Like let's make it look more beautiful. So pi 2, that is equal to mu over rho vd. And for the student who took fluid mechanics and the hydrology and hydraulics, does this look familiar? Little bit, except that it is just like the other way around, yeah? So like if I just make pi 2, let's say like I will say pi 2 is equal to the inverse of pi 2, like pi 2, oops, is the inverse of pi 2. I will make this guy like the inverse of pi 2, v over d over pi. Now this looks familiar, yes? Uh, Rho vd over mu, isn't this like Reynolds number? And I mean, is this the same? Yes, it is the same, because remember, this is dimensionless. Like the dimension of this guy is the same as the dimension of this guy. So the dimension of this guy, like the dimension of viscosity, is ml minus 1 t minus 1 me just do it. Make it look like the dimension of this guy m l minus 1 t minus 1 over, like if you did the dimension of this guy, that would be ml minus 1 t minus 1. So it really doesn't matter because this is like dimensionless. I can flip it up and down. So basically I just like express this as we have here, and we know that this is called like Reynolds number. Yeah, and you did Reynolds number in your previous homework, so you should be familiar with this. So wow, I just have something very nice right now, because I know that like my pi 1, that's like the drag coefficient, my pi 2, that is the Reynolds number. Yeah, and so basically now I can write my final answer. So uh, remember like let me just like just to remind you, like we have this relationship fd is equal, it's a function of this d v rho and like mu, that's the function of these guys. Yeah, fd, that's like my pi 1. So here I have like this guy here, I have like pi 1, that's like my fd, that is a function of my pi 2, because remember like pi 2 has all these guys, so that's the function of my pi 2. Wow. So now what does this mean? It means that my drag coefficient is a function of a Reynolds number, and that's why we get uh, these like non-linear relationship here, because sometimes you have a laminar flow, sometimes you have a turbulent flow, and basically your drag coefficient will have this like non-linear relationship, whether your flow is like laminar or turbulent. Yeah. Again, if you don't understand like what is laminar flow or turbulent flow, that's fine. I mean, this is not like a fluid mechanics course. I know some of you didn't study fluid mechanics before, so I mean that is fine. It's not like important. What's important is that like you just like learn like how to do pi theorem. So basically, why are we doing again pi theorem? Because we did remember last class we did a review for dimensional analysis, and in this class I'm showing you the application of dimensional analysis for the student in the water program. So basically, they need to know like these details. Yeah. Okay. Uh, So write your final answer. So what is my final answer? So my final answer is I mean I can make this a little bit bigger. So that's like my final answer. My final answer here is that like I have like here the drag coefficient that is equal to ft over rho v square d square. That is like a function of my Reynolds number. That's a function of my Reynolds number, which is equal to rho v d over mu. And I get like this non-linear relationship, yeah, which is not unexpected, yeah. I can write it also, that's my final answer. I could also write it like, I would also write it like to write it this way, like pi 1 is a function of like pi 2, yeah. Again, that is like CD, my drag coefficient, is a function of like our Reynolds number. That is like my drag coefficient is a function of rho v square d square. That's like a function of rho v d and mu. Yeah. So I ended up with this relationship, and basically that is what I need to do in the lab. So in the lab, I could change like these guys, like rho vd and mu, and measure f, and that would be 1 point here, and then change it again, measure it, and there'll be another point here, another point here, another point. So I keep making these measurements, and every experiment I will do, I just can plot it here and in this figure here. Yeah, I can just like plot it here on this figure. So I can just plot my drag coefficient divided by this and my renal number like this divided by this, and then I got this relationship. Like, how could I find like this constant? Remember, this is like this basically like all I'm saying here. Like, this is like CD is proportional. Remember, we did this before to RE. Yeah, and like to get rid of this proportionality, I can say it like CD that is equal to some constant here. RE, like how to find like these constant, like this proportionality constant, then like for each regime, like you can find like this proportionality constant, and you will have like different equation, whether like laminar, whether it's turbulent, and so on and so forth. But this is not important for what we are doing here. So this is just like for your own information in case you are wondering. But this is not important for like dimensional analysis and for scaling. So I think that's the end of this lesson. It was short. We did a lot actually. You learned a lot. I was able to compress it in hopefully less than an hour. Let me check the time. Wow, it's only 30, less than 40 minutes actually. I was able to explain like a pi theorem and dimensional analysis, which is very good. If you have any questions, just let me know. If it is something is unclear or you want more detail, just let me know in the exit ticket. So you remember, like after each lesson, you have to do an exit ticket. So for lesson 2, so far you have 2 exit tickets. So you have exit ticket for like part 1 and then exit ticket for part 2. If you have nothing, no comment, thank you is always appreciated. Yeah. If you have some comments, just write them down and I will respond to your comments. Okay. So yeah, so see you in part 3. So in part 3, that is like the fun part, which is like now we have this pi term, like we have this here is like pi 1, yeah, and this is here, that's like my pi 2. This is like this called like dimensionless parameter. So I have like this dimensionless parameter and I have this dimensionless parameter. Next lesson, we will learn how to, like, so this lesson, we learned how like to do this, like to design experiments and like represent the experiment results as just in one graph like this. Next lesson, I will show you like how to use this pi term. I will explain to you something called like the scaling law. So how could you basically scale from these experiments that you are doing in the lab to your actual system, like the actual column of that bridge that I showed you in the real world. So that we will do this next class. I will show you like how to use this pi term. So this is pi 1 for like your model, like your physical model. This is pi 2 for your physical model. For your physical model, like how could you scale this to pi 1 for like your prototype, like your actual system, and how you could scale this guy for like your actual system, so as to know, like for example, like scaling this one to the actual system, that would be very useful, because now if you measure this force in your model with this diameter, then you can scale it back and know what will happen to the actual system or the actual object. Yeah. That's the importance of scaling. So we will do this like next class, and we will solve like a practical problem, and then we will do one problem related to environmental engineering and water resources engineering, like to that would be a practice problem basically. Like I will like do one drag force related to like a vehicle or something, a simple problem, and then your practice problem would be a problem related to water resources and slash environment.